What have a 60-foot female humpback whale and a battery got in common? Turns out, quite a lot. The female humpback migrates 25,000 kilometers to give birth in the tropics. In that time, she eats nothing, turning herself into a 30-ton energy store of blubber. After birth, she directs almost all this energy to feeding the little one. But not all of it. She keeps back only enough energy reserves to keep herself going, to allow her to continue to operate as an effective mother. Well, batteries are an energy store, and interestingly, they hold some back too, admittedly for very different reasons. Let me explain. This is Think 4. When you study physics, you make a lot of circuits, but they don't always go to plan, and they don't always produce results exactly as you might expect. One thing you may have noticed is that if a battery is labeled 3 volts, it will never produce a potential difference of 3 volts across a circuit. This is because, like anything that carries electrical charge, it has some resistance. We call the resistance the battery itself has its internal resistance, because it is the resistance within the battery. If we set up a circuit like this, with a battery stamped with 9 volts on it, 9 volts is what we call the EMF, or electromotive force. This is the energy given to each coulomb that passes through the cell. If we use a voltmeter to measure the potential difference across the battery, you may think this is the energy produced by the battery per coulomb of charge. You are actually measuring the energy used in the rest of the circuit. When it is switched on, we call this the terminal PD. The difference between the EMF and the terminal PD is what we might call lost volts. This is the energy given to the charges that is used up just traveling through the battery. So we could say EMF equals terminal PD plus lost volts. We would write this mathematically as EMF, or E, equals VTPD for terminal potential difference, plus V lost for the voltage lost as a result of the internal resistance of the battery. As V equals IR, and we know that the current will be the same anywhere in a series circuit, we can substitute I lowercase r for the volts lost to give us the relationship E equals V plus IR. To more easily demonstrate the internal resistance, we often draw the circuit to include a resistor next to the battery to show its internal resistance. And in higher physics, there is often a switch included in the circuit, which when open would mean no current flows. If we have a voltmeter measuring the potential difference across the battery when no current flows, we would measure the EMF. This question is a good example of the type of problem you could face. When the switch is open, the reading on the voltmeter is 1.5 volts. This indicates the EMF of the battery, which is the answer to part 1 of the problem. Part 2 asks us to calculate the internal resistance of the cell. In this case, we know the EMF, the current in the circuit, and both the terminal PD and the volts lost, which will be 1.3 and 0.2. If we use the equation E equals V plus IR and substitute in our values, we get 1.5 equals 1.3 plus 0.88 multiplied by internal resistance. To calculate R, we subtract 1.3 from 1.5 and divide through by 0.88 to give us 0.23 ohms. So there you have it. Batteries and the natural world have a lot in common. Both require energy stores, and both use a proportion of their own energy too. I would suggest, however, the energy needed to migrate 25,000 kilometers would require a pretty big battery. And as far as I know, they haven't invented that yet. This was Think 4. Thanks for watching.